Okay, good evening and welcome everybody to this evening's webinar organised by the Energy, Environment and Climate Action Division of Engineers Ireland. My name is Barry McMullen. I'm currently the chair of the division, and it's my pleasure to introduce this evening's event. It's a hybrid event. We have an audience, a select audience here in Clyde Road, and thanks to those people who turned out on a rather wet and windy afternoon or evening here today. But we have had a lot of interest in this evening's event and quite a large audience online, so you're all very welcome indeed. For those who aren't in the room, you don't need fire safety advice, but for those in the room, in the unlikely event of an emergency, you just follow the signs. For those who are not in the room, just the housekeeping information is that if you want to line up questions during the session, please use the Q&A facility in Zoom, and we'll moderate the questions at the end. The main presentation will be recorded and made available afterwards. We don't record the Q&A part of the session, but the presentation will be recorded and made available afterwards. So with that preamble, it's my pleasure to welcome and introduce Dr. Ciara Beausang. Ciara has been researching in the area, particularly of anaerobic digestion, for the past number of years, and completed her PhD now 2 years ago. 2 years ago, and did a really deep dive on aspects of anaerobic digestion as it applies specifically to Ireland. Obviously, anaerobic digestion is a relatively mature technology. It's widely deployed, but there's a lot of devils in the detail of exactly how it's operated and the particular circumstances in any particular country in terms of feedstocks and the way the system is managed and what use is made of the biogas produced and so forth. So we're really looking forward to a great deep dive into this evening, but with that, I'll hand over to Ciara. Thank you.
Thanks very much for the introduction and the invitation to be here, Barry, and good evening to everyone here in the audience and those who are joining us online. So the title of my presentation this evening is Anaerobic Digestion in Ireland, Environmental Risk versus Reward. So just to give you an outline of my presentation, I think if my clicker is working. Oh, there we go. So I'm going to give you a brief overview and a little bit about the context of anaerobic digestion in Ireland, what it may look like as a technology here. I'm going to talk about the current resources that are available for anaerobic digestion in Ireland and the potential scale that could reach and the targets that have been set. I'm then going to talk a little bit about the environmental impacts of the technology, which is the main area of my research to date. And particularly focusing on feedstocks and methane leakage, and then maybe zooming out finally to the big picture and seeing what that looks like. So maybe to take a rather philosophical question for a Wednesday evening, why are we here? Well, I think the reason that we're talking about anaerobic digestion as a technology is because of the climate emergency that we're in. So the UN Environmental Programme released their report just last week, the emissions gap report for 2022, and it found that currently there is no credible pathway in place to limit global warming to 1.5 degrees Celsius in accord with the Paris Agreement. Currently, with the pledges from all the countries that are on the table, we're looking at about 2.8 degrees of warming by the end of the century, which is astonishing and very, very frightening. So you can see we see these headlines quite regularly, and you know, I myself am good at sort of getting used to them and ignoring them, but I think it's worth stepping back and considering why are we talking about this technology in the first place, and what potential does it have? So what is AD? So anaerobic means without oxygen, and digestion means organic matter that's broken down by microbial activity. So here we have an overview of anaerobic digestion as a technology. So you can see we have organic feedstocks that are fed into a digester. And the main feedstocks that have been identified in an Irish context that have good potential for anaerobic digestion are mainly slurry and manure, crops and crop residues, and food waste. So anaerobic digestion, it's quite a sensitive process. You have to be quite careful with the balance of feedstocks that are feeding into the digester. We can't use, woody biomass or things like that because it won't be broken down by the bacteria in the tank. And even in the context of things like food waste, we have to be really careful in terms of removing plastic packaging and things like that before it can be fed into the digester. So our biomass is fed into the digester and it's broken down by the bacteria. And the main product that's produced is biogas. So biogas consists of about 60% methane, and the rest is about 40% carbon dioxide. And I suppose traditionally the main use in Europe for biogas would have been in combined heat and power units, and that would be for the production of electricity and heat. And as Barry mentioned, I suppose the technology is a little less mature in Ireland and hasn't been deployed to the same extent. And there's more interest, I think, now in the potential of upgrading biogas to biomethane. So that means removing the carbon dioxide or stripping it and purifying it. So we have biomethane, which consists of about 99% methane. And I suppose there are two main pathways for how that biomethane can be used. The first is injected into the gas grid as a renewable gas. And the second option then potentially is looking at a transport fuel in the form of compressed gas. There's also a second product that's produced from anaerobic digestion, and that is the digestate. So that's the solid fraction that's left behind after the material is broken down by the bacteria. And this is a really good source of nutrients. Those nutrients going into the system are retained in the process, and digestate has really good potential as a biofertilizer, but needs to be carefully managed, as we'll see later on. So that's sort of an overview of the system I think that we're looking at in an Irish context. So environmental impacts, the benefits of anaerobic digestion, what are the risks versus the rewards? So if we look at the benefits, first of all, obviously anaerobic digestion has good potential as an indigenous form of renewable energy, and that's quite pertinent at the moment, given the fears about energy security we've seen with the events happening with the war in Ukraine, increases in gas prices and concerns about availability. So it's a renewable energy that we could produce domestically in Ireland. As I've outlined from the previous slide, it's suitable for both heat and transport, and these sectors have traditionally been quite difficult to decarbonise in an Irish context. We didn't meet our renewable energy targets in the heat and transport sectors for 2020, so there's good potential for both of those uses. It also offers improved waste management as a technology. So for example, the food waste that's fed into the digester, that offers a benefit if that otherwise may have been sent to landfill and those gases are released from the landfill into the environment. If we're able to capture some of those gases, that has a benefit. And also in terms of managing animal manures, again, if we're capturing some of those emissions that may otherwise have been lost, that's a benefit of the technology. And finally, as I've mentioned, the digestate that's left over is valuable as a biofertilizer. So you can see it's quite a multifunctional technology and there are quite a number of benefits. So if we just have a look at what sort of feedstocks may be available and what sort of quantities they're available in an Irish context, this data is taken from the National Heat Study, and the particular report is the Sustainable Bioenergy for Heat by SCAI. And you can see here that the main resource that's contributing to biogas potential in Ireland is largely coming from cattle slurry and grass silage. So I think over 75% actually of the main resource is coming from those feedstocks. And that's primarily the grass silage with some benefits from the cattle slurry being added. And a smaller proportion then coming from other feedstocks like domestic, commercial and industrial food waste. and also pig slurry. So I suppose one of the advantages of pig slurry as a feedstock is that the farms are quite concentrated in terms of having a large number of animals and more of the slurry being captured from indoor systems. So that's why that comes up as a notable resource. So what kind of scale are we talking about in an Irish context? I think sometimes this is something that's difficult to visualize. So here you can see an example of the Teagasc pilot plant, which is based in Grange, County Meath. So this is a 500 meter cubed digester, and it's due to be commissioned early next year. And the idea is that this digester will co-digest grass silage and cattle slurry. So it will require grass silage from about 70 hectares and the slurry from 1,000 cattle. So it's quite substantial. It's not necessarily, for this size of plant, a farm scale technology. You're going to have several farmers feeding into a centralized system to supply a plant like this. And the output from a plant of this size annually would be about 3.2 gigawatt hours. So then if we consider some of the targets that are being discussed for biomethane in Ireland, so in the 2021 Climate Action Plan, a target was set there of 1.6 terawatt hours of biomethane. And then in the industry-led initiative Project Clover, which is a venture by a number of dairy processors, they have set a target of 2.5 terawatt hours. So the scale that they're considering is larger plants, which would be 20 gigawatt hours. So you're looking at about 125 plants of those size. And what would that require in terms of 2.5 terawatt hours? Well, you'd be looking at about 5% of the grass silage that's currently being produced annually, and about 4% of the slurry that's currently being captured. So quite a substantial amount of feedstock that would have to be mobilized for that target. The sectoral emission ceilings were announced by the government in July of this year. And in that announcement, they made reference to additional resources being made available for anaerobic digestion. And they indicated a target of up to 5.7 terawatt hours of biomethane. And that would constitute in and around 10% of the current natural gas supply. So you can see that's quite a scaling up again, going from 1.6 to 2.5 to 5.7 terawatt hours. And you know, there would be a lot needed to be done there to mobilize that scale of industry and to get it off the ground. So if we consider then the environmental impact of biomethane, so I conducted a life cycle analysis of grass biomethane, and specifically looking at the greenhouse gas emissions that are associated with its production. And this is shown in the bar chart here. So you can see about 75% of the emissions are coming from fertilizer. So that's both in terms of production of fertilizer and agrochemicals, and then their application on the land. So that's the orange bar, and that's the field N2O emissions of nitrous oxide when the fertilizer is spread on land. And then a substantial portion as well is coming from methane losses. So when I conducted this analysis, I used a figure of 2.4% methane losses coming from the overall production of biomethane. And that was based on a study in Denmark, which looked at the average losses from, I think it was 13 biogas plants, of agricultural biogas plants. So the methane losses are quite an important consideration as well. Obviously, methane is a powerful short-lived gas, and any leakages that occur from biogas production are going to have a negative environmental impact. And they're also going to have a negative impact economically for a biogas producer. So if we consider then, what are the potential risks associated with the technology? Well, I think there are probably 4 areas to consider. And that would include feedstock provision, the methane leakage, managing digestate, and then considering the pathways for decarbonisation. So in terms of the feedstock provision, so as I've outlined, grass silage is one of the main resources that has been identified for biogas potential in an Irish context. And I suppose there's a question around how we're going to provide additional grass silage that's surplus to livestock requirements, because we don't want to be competing with food production. So I suppose there are 2 possible scenarios in order to achieve this. First consideration might be looking at reducing animal numbers, and that was a scenario that was considered in the HEAT study by SEAI. So they were assuming that in one scenario, there may be a reduction in the suckler herd, and that might make more land available for grass silage production for biomethane. An alternative mechanism to provide that surplus grass silage would be to increase yield on existing land. And there are two mechanisms potentially to do that. One would be through additional nitrogen fertilizer, so increasing the overall amount of nitrogen fertilizer that's applied, or alternatively, looking at the potential of incorporating legumes such as clover and using multi-species forage to try and increase yields without the addition of nitrogen fertilizer. And I'll discuss that in a little bit more detail. So I did some analysis looking at the impact of silage production, and I looked at different species of forage and how they may look like in terms of the sustainability of the biomethane that's produced. So perennial ryegrass is the standard forage that's produced on Irish grassland. It's the main species that we have. It produces very good yields, but it does require substantial inputs of inorganic nitrogen. So that was the first type of forage I considered. It was receiving about 120 kilograms per hectare of nitrogen. And you can see the yields here that are reported for these forages are based on work by Thomas Maloney. The second type of forage I considered was perennial ryegrass that incorporated red clover. And you can see in this instance, this forage wasn't receiving any inorganic nitrogen, but still achieving a relatively good yield of dry matter, so 10,000 kgs per hectare. And the third type of forage I considered was a multi-species forage. So that would have a number of different swords or types of forage included in it, including perennial ryegrass, clover, and also some other herbs like chicory and plantain. And again, this didn't receive any inorganic nitrogen and achieved quite a good high yield of dry matter. And the final column on the table compared to the greenhouse gas emissions produced. So it's reported in terms of grams of CO2 equivalent per megajoule of biomethane. So this is the standard unit that we use when reporting under the Renewable Energy Directive. And you can see that the emissions associated with perennial ryegrass and red clover and also the multi-species swords are substantially lower than the perennial ryegrass on its own. And that's mainly down to the exclusion of the inorganic nitrogen fertilizer. So we can see that this approach does have some benefits in terms of reducing the inorganic nitrogen input, but still maintaining good yields. And that could help, hopefully, or potentially help to provide additional grass silage if it was to be used for this technology. Another consideration in order to provide the surplus feedstock for anaerobic digestion would be to look at the potential of biorefining. So this figure is based on research that was done by the Biorefinery Gloss project, and that was led by Munster Technological University. So this was looking at the potential of refining fresh grass and fractionating it into a solid fraction and a liquid fraction, so a press cake and a juice. So the press cake has good potential to be used as cattle feed, and the juice can be fractionated into a number of different components, but you can see on the end there, whey is one of the products that's produced, and again, that would have potential for bioenergy. So this kind of approach is quite sensible, I think, in terms of the bioeconomy, where we're trying to use our biological resources for the highest value in the first instance, and then following a cascading approach down for the different energy uses. So we're still providing sources of feed output in the first instance, and then following down the chain, having some outputs that could be used for bioenergy production. And the next slide just gives you a picture of what the press cake looks like. So the solid fibrous fraction and the juice looking a little bit like a green smoothie. Don't know what it would taste like. So we can see there are technologies available that could potentially increase grass silage production and have surplus grass silage excess to livestock requirements. But it does raise the question of, are we using our land for the best potential use? And we know that land management has a key role to play in response to climate change. And currently land use change in forestry, or LULUCF, is a net source of carbon in an Irish context. And in particular, the drainage of organic soils is the main source of carbon that's coming from that sector. Currently, our forests are a sink, but because of low planting rates, this is a risk for our carbon sink in the future. So we're going to have to be careful and consider carefully how best we're going to use our land. And there was an interesting study done by David Stiles looking at the climate mitigation efficacy of anaerobic digestion in a decarbonising economy. Now, this study was based on the UK, but it compared different land uses compared to anaerobic digestion. And one of the findings is that solar electricity generation can avoid 16 times more fossil energy compared to grass biomethane transport. And this is on the basis of per hectare of land occupied. And similarly, afforestation can mitigate 6 times more greenhouse gases per hectare of land occupied compared to grass biomethane as a transport fuel. So I think there are going to be challenges going forward in terms of identifying what the best potential uses for our land is, considering the different targets that we're going to have to achieve under the sectoral emission ceilings. So if there is excess land that could potentially be made available by increasing grass yields, it begs the question, is it the best use of that land for additional grass silage for biomethane production, or should alternative uses like solar PV, like afforestation? And that's a much bigger discussion, I think, to be had ultimately in terms of, how farmers want to use their land. Are they being rewarded, financially for doing the environmental, best thing on a case-by-case basis? So I'm going to talk briefly now about methane leakage, also referred to fugitive methane emissions. So methane leakage is generally expressed in terms of emission factors, and that's relating the emitted gas quantity to the overall amount of gas that's produced. And often a 1% loss is assumed in life cycle assessments by default. But as I've highlighted in the life cycle assessment piece earlier, the methane leakage is quite an important part in the overall life cycle of biogas and biomethane production. So it's important to consider what higher leakage rates might look like and what impact that would have on the overall environmental sustainability. So this was a project that was done in Europe, evaluation and reduction of methane emissions from different European biogas plant concepts. And there are a number of partner countries, including Germany, Austria, Switzerland, and Sweden, who again would probably have quite established biomethane and biogas industries compared to Ireland. So in that project, they compared on-site and off-site approaches in order to measure and detect methane leakages. And those different approaches would enable you to look at individual sources of emissions coming from a biogas plant, and then also trying to determine the overall rate of emissions coming from the plant as a total. And they found in their research across a number of different plants in the partner countries that there is a potential leakage rate of between 0.1 to 50 kgs of methane per hour, which is quite substantial. And this related to about 0.4 to 11% of total biomethane production. So the biomethane leakage or the methane leakage can be quite high, and it's something that needs to be monitored quite carefully. The main emission sources that have been identified for biomethane leakage occur in terms of the individual leakages that are detected. They mostly occur at the roof of the digester. And very often, this can be a case where there's simply too much biogas being contained in the tank, and it's putting pressure on the membrane on top of the tank. And moderating the amount of gas in the tank can help manage any leakages. The next most significant source is digestate storage. So open and non-gas tight storage tanks were found to be a major source of methane leakage. And again, there's quite a simple solution there, where you have gas tight or closed or covered tanks that will help to mitigate any emissions. And finally, the pressure release valve is another significant source. And obviously this would be something that's outside of normal operating conditions. And it comes down to, again, if the tanks are overfilled, the valve is put under more pressure and there's more leakages. But as I've outlined, many of these emission sources can be reduced simply by changing the operating procedures. And it points to the need for regular leakage detection in plants, and critically gas-tight covering of digestate storage tanks. And it also underlines the importance of regular maintenance. And the research in Europe pointed to the value of voluntary schemes and also operator training to make sure that the emissions are minimized. Just in terms of some of the other environmental impacts, digestate management is quite an important consideration for the overall sustainability of biogas production. So as I mentioned, digestate is quite valuable as a biofertilizer, but it is usually found to have higher levels of ammonium, and that's due to the process it's been through in terms of anaerobic digestion. And that poses a risk where that ammonia is more available and can be released into the environment when it's spread on the land. So this points to the need to use low emission slurry spreading by default as the method to apply digestate back to the land from anaerobic digestion plants. And if we're just to zoom out and maybe consider the bigger picture, this graph is taken from a report, I think it's from 2018 from Gas Networks Ireland called Vision 2050, where it was looking at the potential for a net zero carbon gas network by 2050. And you can see the blue portion there is looking at natural gas, pointing to a reduction over time. The green portion, or the dark green portion, is looking at biomethane. The lighter green is looking at abated natural gas, and that's with carbon capture and storage. And then finally, the yellow is looking at hydrogen. So you can see there's quite a considerable amount of natural gas in the gas grid, all the way up until, well past 2030, and a smaller amount of biomethane that's penetrating through. Now, this report, I think, was based on earlier targets for biomethane injection into the grid. But I suppose what this figure is pointing to is that the whole decarbonisation of the gas network needs to be taken into account, and not just the biomethane on its own as a renewable gas. So we need to have everything working in tandem to achieve a net zero gas grid. So it points to the need for, increased hydrogen production. It shows here the dependency for abated natural gas with carbon capture and storage. And I think all of those parts will have to be working for it to make sense to have, biomethane production at scale. If we consider briefly then maybe some of the other uses for biomethane, obviously, as I mentioned before, it has good potential in transport. So that's in the form of fueling vehicles with compressed natural gas, or CNG. And there's also probably a consideration there in terms of decentralized uses for biomethane. So looking at large energy users, particularly in food and beverage industry, there may be potential in using biomethane in off-site decentralized systems where we're not depending on the existing fossil fuel infrastructure of the grid to supply the renewable source of energy. And I think there's been particular research done looking at distilleries in Ireland and the potential of biomethane in that context. So if we're to consider then, I gave a very provocative title, environmental risk versus reward. Well, what's the answer? Is it more of a risk? Is it more of a reward? And I think if we're to zoom out and consider all of the things that have been discussed, it really comes down to striking a balance between all of the systems that are in place. So if we consider the wider decarbonisation of energy systems, we're going to have everything working in tandem to make sure that the success of a decarbonised gas grid is possible. And it also points to the need to consider reduced energy demand. So the targets that I've mentioned, 5.7 terawatt hours, that constitutes 10% of the current gas supply. It's going to make little sense if we're trying to produce biomethane on top of increasing demands for gas. So energy demand is something that's going to have to be addressed. It also points to the need for sustainable agricultural systems, and it's going to depend very much on the uptake of the different technologies that I've outlined already. So that includes, the likes of the multi-species swards, the use of the low emission slurry spreading. It's also going to have to consider things like, soil fertility and fertility programs, and that's all dependent on uptake by farmers. And I guess there is also a consideration in terms of the types of agricultural systems that are supporting biomethane. So if we have a dependency on livestock agriculture to supply the necessary cattle slurry to feed the plants, there's a question then about the reaching the targets in that sector and whether that's attainable. And if we look on the other side, then certainly, as I've outlined, anaerobic digestion is a multifunctional technology. There are many benefits that come with it, particularly with the likes of the waste management and the provision of Digestate as a biofertilizer. And we may be actually adding value to our manures and slurries by putting them through the AD process and making the nutrients more available, but it has to be carefully managed. And finally, it does have good potential in particular sectors, as I've mentioned, like heat and transport, that have been traditionally hard to decarbonise. But I think there's a question again about scale. How quickly can we get this technology up and running in an Irish context? It's certainly going to be a challenge. So I think this is my final slide. Thank you very much for your attention, and I look forward to your questions.